Ooh, welcome to the wonderful world of Alkene addition reactions. So today we're going to be looking through two different examples. We're going to be predicting the products of alkene addition reactions, and then we'll take a closer look at the electron pushing mechanism that makes each of them possible. So as a quick recap, here's our strategy for evaluating alkene addition reactions that we'll be looking through. The strategy will generally be very useful in predicting what products you can expect from a reaction. First, really the heart of the reaction comes down to the carbocation intermediate and its stability. So we're going to look at hyperconjugation. Remember that a tertiary carbocation is more stable than a secondary carbocation, which is more stable than a primary carbocation. Then, after we have our intermediate, we'll ask ourselves, is there a more stable intermediate that we can make? Is there the chance for a hydride shift? And then finally, we will finish off the reaction. So let's take a look at some specific examples. Okay, so here we have this cyclic alkene, and we're reacting it with HCl. How can we predict what products will be present? So first, if we look where our alkene is, right there, let's take a look at the possible carbons that could take on the positive charge of the carbocation when we do the addition reaction. There's this one here, which is secondary. And there's this one here, which is also secondary. So between the two of them, neither one of these carbons is particularly better suited to take on a positive charge. So we could have two possible intermediates that form. We can have this one, where we plop the positive charge on that carbon. Or we could produce this one here, where we put the positive charge on the other secondary carbon. So both of these are possible, and both of them can lead to their respective products. But then we want to ask, is a hydride shift in play for either of these intermediates? So for this first one right here, if we look to the adjacent carbons right next to the carbocation, we can see that they are both secondary. So there's no practical purpose to doing a hydride shift in this case. But if we look at our other carbocation intermediate, we can see that right here, immediately adjacent to the carbocation, is a tertiary carbon. A tertiary carbon would be better suited for taking on the positive charge due to hyperconjugation stability. So, what's going to happen? Well, a hydride shift can occur to make the most stable intermediate possible. And that would look something like this. Our positive charge could go right there. Okay, now that we can envision our intermediates, picturing what the products is going to be much more straightforward. Remember that if we're treating something with HCl, the first step is forming the carbocation intermediate, and then the next step is the chloride coming in and adding into the carbocation site. So we're just going to draw our three intermediates essentially, except instead of having the carbocation positive charge, they're going to have chlorides there. So we'll have this possible product from the intermediate that we've arbitrarily labeled A. We'll have this possible product from the second intermediate. And then finally, we'll have this possible product from our most stable intermediate, the tertiary carbocation. And because this one comes from the most stable intermediate, it's also going to be the major product. So these are our three possible products from this reaction. Now let's take a closer look at the electron pushing that makes this all possible. Our first step of any alkene addition reaction is going to be a nucleophilic attack. The alkene is going to serve as the nucleophile and the acid as the electrophile. So we're going to draw our electron pushing arrow like so, and these electrons are going to jump onto the chloride. And we're going to end up with either this, and just notice that I've drawn in the hydrogen here that was taken from the acid. Not necessary, but just for your records and reference. Or this. So here are the two initial possible intermediates, and once they are formed, this reaction could either finish up, so let's just draw the electron pushing for that, So this chloride could perform a nucleophilic attack to make our first product. Or, if we had the lower intermediate, once again we can have a nucleophilic attack to form our second product. But remember, for this particular intermediate in the bottom left-hand corner, there also exists the potential of a hydride shift. So the way that would occur is on this tertiary carbon, there is a hydrogen that wasn't explicitly drawn in. And the electron pushing here, really pretty straightforward. These electrons just jump over to the carbocation. And basically it's like one giant electron rope that's holding in this hydrogen. So the hydrogen's swinging along with it. It's coming along for the ride. So then we'd be left with this, the most stable of our carbocation intermediates, due to the fact that it's tertiary. And then the last step would just be the chloride performing a nucleophilic attack on that tertiary carbocation to give us our most stable product, this fellow right here. Okay, now let's take a look at what happens when we treat an alkene with sulfuric acid and water. So first, let's just predict what the product would look like. Once again, the key to these problems lies in envisioning what the carbocation intermediate would look like. So if we consider our alkene, we have a tertiary carbon here, and we have a primary carbon right here. One of those is much better suited to get a positive charge, and that is the tertiary. So when we draw an intermediate, it's going to look like this. Okay, so then we check, is there any hydride shift available? Well, if we look at our neighboring carbons, we've got this one here, which is primary. We've got this carbon here, also primary. Neither of those are more stable. And then we've got this carbon over here, which is actually quaternary. Okay, so we can perform a hydride shift with a tertiary carbon, but a quaternary one, that can't happen. Why is that? Well, this already has its 1, 2, 3, 4 bonds to carbon. There's no hydrogen there to perform a hydride shift. So this is out of play. And we can't do a shift here. So it looks like our carbocation intermediate is fine as is. Then we just need to remember that if we're treating with sulfuric acid catalyst and water, that what we're doing is turning an alkene into an alcohol. So how does this take place? Let's look at the play-by-play analysis. First, just like our halogenation reactions, the first step is going to be the alkene acting as a nucleophile, grabbing onto a proton, and these electrons jumping over here to form our first batch of intermediates, our carbocation intermediate, and bisulfate. Okay, so what happens next? Well, the bisulfate is too large to add itself in. So it's not going to be like the reaction that we just looked at where the chloride then acts as a nucleophile. Rather, what's going to happen now is we're going to have water come in and perform our nucleophilic attack instead. It's much more easy for the water to access this carbocation intermediate. So it's going to come in and attack right there. And we'll be left with our next set of intermediates. So here we have our protonated alcohol. And then the last step is just going to be, whoop-pow! The bisulfate strikes back. So this is just going to do an attack here. Grab onto that proton. These electrons are going to jump onto our oxygen. And we'll be left with our alcohol product and our sulfuric acid catalyst. It has been regenerated. So now it can facilitate the reaction over and over and over and over again. And that is the step-by-step playbook of how an alkene turns into an alcohol through this nucleophilic addition reaction. So that's the end of this little video tutorial. I hope that you found it useful and hope that you have a wonderful day.